Chapter 1. The Dream. There is a reactor 30 miles south of Detroit that came within hours of making 2 million people evacuate their homes. It sits on the shore of Lake Erie in Monroe County, Michigan, a low concrete structure surrounded by chain-link fence and farmland. Unremarkable except for what it represents: the moment America's nuclear ambition collided with the laws of physics and almost lost. The reactor's name was Fermi 1. It was not designed to simply generate electricity. It was designed to solve the energy crisis of the future by breeding more fuel than it consumed, a perpetual motion machine for the atomic age, plutonium creating more plutonium in an endless cycle. Until October 5, 1966 at 3:09 p.m. Eastern Time, when something blocked the flow of liquid sodium cooling the reactor core. Temperature spiked to 700 degrees Fahrenheit above normal. 2 fuel assemblies began to melt. The operators had no idea what was happening. Their instruments showed impossible readings. Radiation alarms were screaming, and 30 miles away in Detroit, 2 million people went about their afternoon completely unaware that a decision was being made whether to evacuate the entire city. This is the story of Fermi 1, how it was built on the promise of infinite energy, how it operated at the edge of what physics allowed, and how it almost became the worst nuclear disaster in American history. The Breeder Dream. In 1951, a group of scientists at Idaho National Laboratory achieved something revolutionary. They built a reactor that produced more fuel than it consumed. The experimental Breeder Reactor 1 used fast neutrons to convert uranium-238, which is not fissile, into plutonium-239, which is. While generating electricity, the reactor created new fuel. If scaled up, this technology could extend uranium reserves for thousands of years. The concept was elegant. Natural uranium is 99.3% uranium-238 and only 0.7% uranium-235, the fissile isotope that conventional reactors use. Breeder reactors could utilize the 99.3% that was normally waste. The energy locked in uranium-238 could power civilization indefinitely. The problem was engineering. Breeder reactors required fast neutrons, which meant no water moderator. Water slows neutrons, which is necessary for conventional reactors, but prevents breeding. Fast breeders needed a different coolant, something that wouldn't moderate neutrons but could transfer heat efficiently. Liquid sodium was the answer. Sodium has excellent heat transfer properties and doesn't slow neutrons significantly, but it also reacts violently with water and burns spontaneously in air. Using liquid sodium as reactor coolant was like building a power plant filled with a substance that explodes on contact with the 2 most common materials in the environment. American nuclear engineers believed they could manage these risks. The potential reward, infinite energy, justified the engineering challenges. In 1955, the Power Reactor Breeder 1 was constructed.
Development Company was formed to build America's first commercial-scale breeder reactor. The company was a consortium of utilities led by Detroit Edison. Their vision, a 300-megawatt thermal breeder reactor that would demonstrate the commercial viability of the technology. They named it Fermi 1, after Enrico Fermi, the physicist who had created the first controlled nuclear chain reaction in 1942. The site. The location selected for Fermi 1 was Laguna Beach, Michigan, a strip of land on the western shore of Lake Erie, 30 miles south of Detroit. The site had advantages. Lake Erie provided unlimited cooling water. The land was relatively inexpensive, and it was close enough to Detroit to connect to the electrical grid without extensive transmission infrastructure. It also had a significant disadvantage. It was 30 miles from a major population center. If anything went wrong, 2 million people would be in potential danger. The Atomic Energy Commission, responsible for licensing nuclear facilities, was deeply concerned. In 1956, they held hearings on whether to approve Fermi 1's construction. Labor unions, environmental groups, and some scientists testified against the project. Walter Reuther, president of the United Auto Workers, argued that building an experimental reactor so close to Detroit was reckless. If the reactor experienced a catastrophic accident, the entire metropolitan area could be contaminated. Evacuation might be impossible. The human cost could be staggering. The AEC's own Advisory Committee on Reactor Safeguards was split. Some members believed breeder technology was worth pursuing despite risks. Others argued that a prototype breeder should be built in a remote location far from population centers until the technology was proven safe. Power Reactor Development Company countered that the reactor was designed with multiple safety systems. The containment building could withstand any credible accident. The probability of a major release was vanishingly small, and the economic benefits of breeder technology justified accepting minimal risk. In 1956, the AEC approved construction with conditions. The company would have to demonstrate that the reactor could be operated safely before receiving permission to load fuel and operate at power. This was an unusual arrangement. Normally, construction permits and operating licenses were separate processes. For Fermi 1, the AEC was approving construction while reserving judgment on whether operation would be allowed. Construction began in August 1956. The design. Fermi 1 was unlike any reactor built in America. At its heart was a cylindrical core approximately 30 inches in diameter and 30 inches tall, containing 105 fuel assemblies. Each fuel assembly was a hexagonal stainless steel tube filled with uranium and molten plutonium fuel pins. The fuel was enriched to 25.6% uranium-235, far higher than the 3 to 5% used in conventional reactors. This high enrichment was necessary to achieve the neutron density required for breeding. The core was surrounded by a blanket of depleted uranium. Fast neutrons escaping the core would strike uranium-238 in the blanket, converting it to plutonium-239. This was the breeding process. Over time, the blanket would accumulate plutonium that could be extracted and used as fuel. The entire assembly sat in a pool of liquid sodium. The sodium was heated to 550 degrees Fahrenheit by the fission reactions in the core. It circulated through heat exchangers, transferring heat to a secondary sodium loop, which in turn transferred heat to water to produce steam. The use of 2 sodium loops was a safety feature. If the water-to-sodium heat exchanger leaked, the violent sodium-water reaction would occur in the secondary loop, not in the primary loop containing radioactive sodium that had passed through the reactor core. The reactor vessel was designed to operate at 580 degrees Fahrenheit, hot enough to keep sodium liquid, but cool enough to prevent excessive thermal stress on materials. Temperature control was critical. If sodium temperature rose too high, fuel assemblies could melt.
If temperature dropped too low, sodium could solidify and block cooling channels. The reactor had no control rods in the conventional sense. Instead, control was achieved by moving small sections of the core to adjust neutron density. These control subassemblies could be inserted or withdrawn to regulate the fission rate. Emergency shutdown was accomplished by dropping boron-10 safety rods into the core. These rods absorbed neutrons and would stop the chain reaction within seconds. At least, that was the theory.
Chapter 2. The Meltdown. At 3:15 p.m. on October 5, 1966, 5 minutes after the scram, operators in the Fermi 1 control room were watching their reactor destroy itself. Temperature in 2 core regions continued climbing: 720 degrees, 740 degrees, 760 degrees. The sodium exiting those regions was nearly 200 degrees above normal. Richard Schernbach knew what this meant. Fuel assemblies were melting. The uranium molten plutonium fuel pins were losing structural integrity. The stainless steel cladding was failing. Fission products were escaping into the sodium coolant. This was a partial core meltdown, not as catastrophic as complete core destruction, but severe enough to release massive amounts of radioactivity into the primary sodium loop. The immediate danger was containment. If radioactive sodium leaked from the primary loop, it would contaminate the reactor building. If it contacted water or air, it would burn, potentially breaching containment and releasing radiation to the environment. Schernbach had to prevent that, but he also had to understand what was happening before he could fix it. The impossible readings. The instrumentation at Fermi 1 was showing a pattern that didn't match any predicted accident scenario. Total reactor power was only 67 megawatts when the problem started. After the scram, power dropped to near zero as the fission reaction stopped. Only decay heat remained, perhaps 2-3 megawatts total. But 2 specific core regions were behaving as if they had 10 times more heat than decay heat could produce. Temperature in those regions wasn't declining with the reactor shutdown, it was still rising. This violated basic physics. With the reactor scrapped and sodium pumps still running, temperature should decrease. The sodium should carry away the decay heat. The core should cool. Unless sodium wasn't flowing through those regions. But why not? The pumps were running, flow meters showed normal circulation through the reactor, there was no indication of a pump failure or flow blockage. One engineer suggested the instrumentation might be malfunctioning. Perhaps there was no actual overheating, just false readings from damaged instruments. Schernbach considered this. Instrument failures were common. They dealt with erratic sensors before. But radiation monitors in the containment building were showing elevated levels of fission products. This was independent confirmation that fuel was failing. The instrument readings weren't false. Something really was overheating. At 3:20 p.m., 10 minutes after the scram, temperature peaked at 770 degrees Fahrenheit in the hottest region. This was 190 degrees above normal. At these temperatures, fuel assemblies were definitely melting. Then, finally, temperature began to drop, slowly at first, then more rapidly as whatever had blocked sodium flow apparently cleared or as the fuel damage reduced heat generation. By 3:30 p.m., temperature was back to 600 degrees, still elevated but declining.
Steadily, the immediate crisis was passing, but the reactor was damaged. The question was, how badly? The contamination. While operators monitored core temperatures, health physicists were tracking radiation levels throughout the facility. The primary sodium loop, which circulated through the reactor core, normally contained some radioactivity from neutron activation of the sodium itself. This was expected and manageable.
But now, with fuel assemblies damaged, the primary sodium contained fission products, iodine-131, cesium-137, xenon-133, and dozens of other radioactive isotopes that should have remained sealed inside fuel pins. The contamination was severe. Radiation levels in the primary sodium system measured 100 times higher than normal. Any leak in this system would release intensely radioactive material. The containment building atmosphere showed elevated levels of noble gases, primarily xenon and krypton. These gases had escaped from damaged fuel, dissolved in the sodium, and then degassed into the building atmosphere. Radiation monitors outside the containment building showed normal background levels. The containment was holding. No radioactive material was escaping to the environment. This was critical. As long as containment integrity was maintained, the accident remained contained. The public was not at risk. But Schernbach and his team were making decisions about whether to keep it that way. The decision. By 4 p.m., 1 hour after the incident began, the immediate danger had passed. Core temperature was declining. Sodium flow appeared normal. The reactor was stable, though damaged. Now came the difficult questions. What had caused the sodium flow blockage? Was it a random failure or an inherent design flaw? Could it happen again? How much fuel had melted? 2 assemblies? 10? 50? The extent of damage would determine whether the reactor could be repaired or would need to be permanently shut down. Was there any risk of further damage? If more fuel failed, could it cause a more severe accident? Could it breach containment? Most importantly, should they notify authorities and the public about what had happened? Technically, this was a reportable event. Any fuel failure required notification to the Atomic Energy Commission within 24 hours. Any release of radioactivity required immediate notification. But no radioactivity had been released to the environment. The containment building was sealed. By some interpretations, this was an internal event that didn't require immediate public notification. The decision was complicated by politics. Fermi 1 had been controversial from the beginning. Opponents had predicted exactly this kind of accident. If news of a partial meltdown became public, political pressure to permanently shut down the reactor would be overwhelming. Power Reactor Development Company had invested $135 million. Detroit Edison needed the reactor to justify that investment. The entire American breeder program depended on
Fermi 1 succeeding. A decision was made. They would notify the AEC as required. They would investigate the cause thoroughly, but they would minimize public disclosure, characterizing the event as a minor equipment malfunction, not a partial core meltdown. This decision would have consequences. The investigation. Over the following days, engineers attempted to determine what had caused the sodium flow blockage. They reviewed every instrument reading from the incident. They analyzed the pattern of temperature increases. They examined the reactor's thermal hydraulics to understand how sodium could flow normally through most of the core, but be blocked in 2 specific regions. The data suggested that something inside the reactor vessel had come loose and partially blocked sodium flow. But what? The reactor had been designed with flow channels carefully shaped to ensure uniform cooling. Nothing should be able to move and create a blockage. Engineers created computer models of sodium flow through the core with various hypothetical obstructions. They found that a piece of metal, approximately the size of a dinner plate, if positioned at the bottom of the reactor vessel, could deflect sodium flow away from specific fuel assemblies, creating the observed overheating pattern.
But where would such a piece of metal come from? Everything inside the reactor vessel was welded or bolted securely in place. Components didn't just break loose. Unless something had been installed incorrectly during construction or maintenance, or unless years of thermal cycling had caused a weld to fail. To find out, they would need to look inside the reactor core, and that presented a major challenge. The reactor core was intensely radioactive from years of operation, plus the recent fuel damage. Radiation levels inside the reactor vessel exceeded 10,000 Roentgens per hour in some locations, instantly lethal. Normally, examining reactor internals required removing the reactor head and using remote cameras and tools. But Fermi 1's design didn't allow easy access. The sodium-filled reactor vessel couldn't be opened without draining sodium, and draining sodium risked solidification if temperature wasn't carefully controlled. The investigation would take months, possibly years. The silence. While engineers investigated, the accident remained largely unknown to the public. The AEC received notification as required, but the report classified the incident as a fuel damage from flow blockage, not as a meltdown. The radiation release was characterized as minimal gaseous release to containment, not as a major contamination of the primary sodium system. Local media in Detroit reported briefly that Fermi 1 had experienced a malfunction and was shut down for repairs. The reports cited company statements describing routine equipment problems. No one mentioned that 2 fuel assemblies had melted. No one said that radiation levels in the primary system had spiked to 100 times normal.
Discussed how close the accident had come to being much worse. Environmental groups and labor unions that had opposed Fermi 1's construction suspected the truth. They demanded more information from the AEC. Their requests were met with technical reports written in language that obscured rather than clarified what had occurred. For 2 years, as investigation continued, Fermi 1 sat idle and radioactive. The reactor that was supposed to demonstrate the viability of breeder technology had instead demonstrated how catastrophically such reactors could fail. And 30 miles away, in Detroit, 2 million people remained unaware of how close they had come to evacuation. Chapter 3. The Discovery. In May 1968, 18 months after the accident, engineers finally gained access to the Fermi 1 reactor vessel. The process of preparing for internal inspection had taken over a year. Radiation levels inside the vessel had to decay. Procedures had to be developed for draining and sampling the radioactive sodium. Remote handling equipment had to be designed and tested. When cameras finally entered the reactor vessel on May 24, 1968, they revealed a scene of devastation. The core damage. The fuel assemblies in the central region of the core showed visible damage. 2 assemblies had partially melted. The hexagonal stainless steel cladding had warped and sagged. Some fuel pins had failed entirely, releasing their uranium-plutonium contents into the sodium. 4 additional assemblies showed evidence of overheating. The cladding was discolored and distorted, though not completely melted. In total, approximately 6% of the reactor core had been damaged. This was significant, but not catastrophic. The reactor containment vessel was intact. The majority of fuel assemblies were undamaged. If the cause of the flow blockage could be identified and fixed, the reactor could potentially be repaired. But first, they needed to find what had caused the blockage. Cameras scanned the bottom of the reactor vessel. Sodium had been drained, revealing the core support structure and flow distribution system. At the bottom of the vessel,
They found it. A roughly triangular piece of stainless steel, approximately 24 inches on each side and 6 inches tall, was lying at the bottom of the reactor vessel. It had originally been installed as part of a flow guide, a cone-shaped structure designed to direct sodium upward into the core. This flow guide was not part of the original reactor design. It had been added during construction as a safety feature. Engineers worried that during certain accident scenarios, molten fuel might slump to the bottom of the reactor vessel. The cone-shaped flow guide was intended to prevent molten fuel from collecting in a critical mass that could restart the chain reaction. The flow guide had been installed in 1963, 3 years before the accident. It had operated without problem for 3 years and thousands of hours of reactor operation. Until October 5, 1966, when one of the segments tore loose. The failure mode. Further inspection revealed what had happened. The flow guide segments were attached to the reactor vessel bottom with zirconium bolts. Zirconium was chosen because it has good corrosion resistance in sodium and doesn't become highly radioactive under neutron irradiation. But zirconium also has a property that the designers didn't fully consider. It becomes brittle when exposed to radiation and thermal cycling. Over 3 years of operation, neutron bombardment had changed the crystal structure of the zirconium bolts. They had become progressively more brittle. Thermal cycling, the repeated heating and
Cooling as the reactor started up and shut down, created stress. On October 5th, as operators increased power, thermal expansion created additional stress on the bolts. One bolt fractured, then another. Within seconds, an entire segment of the flow guide tore free. The loose segment, approximately 24 inches across and weighing several pounds, dropped to the lowest point in the reactor vessel. Its position partially blocked sodium flow into the core, deflecting coolant away from 2 fuel assemblies. Those assemblies, receiving insufficient cooling, overheated. Fuel melted. Fission products escaped. Radiation contaminated the primary sodium system. The accident had been caused by a safety feature. The flow guide, installed to prevent one type of accident, had created the conditions for a different accident. The irony. The zirconium bolt failure was particularly frustrating because it had been preventable. During design review in 1962, one engineer had questioned the use of zirconium bolts in a high neutron flux environment. He suggested using stainless steel instead, which was more radiation resistant. The design team rejected this suggestion. Stainless steel became more radioactive than zirconium under neutron exposure. Using stainless steel bolts would increase radiation levels during maintenance, making the reactor harder to service. This was a valid concern, but it prioritized maintenance convenience over structural reliability. The engineer who raised the concern didn't pursue it further. He accepted the design team's judgment. The decision to use zirconium bolts was documented in design records and approved. 5 years later, that decision caused a partial core meltdown. This was a pattern that would repeat throughout nuclear history. Reasonable engineering decisions made with incomplete information leading to unreasonable consequences. The repair decision. With the cause identified, Power Reactor Development Company faced a choice. They could remove the damaged fuel assemblies, repair or replace the flow guide, and restart the reactor. This would cost millions of dollars and take years, but it would salvage the project. Or they could abandon Fermi 1, write off the investment, and admit that the breeder reactor concept, at least as implemented at Fermi, was not viable. The decision was complicated by changing economics. Between 1963 and 1968, the cost of conventional nuclear power had dropped dramatically. Light water reactors, like those at pressurized water reactor plants, were generating electricity reliably and relatively cheaply. Breeder reactors, which were supposed to be economically superior because they created fuel, were proving more expensive than anticipated. The complexity of sodium cooling, the difficulty of maintenance, the risk of accidents like the one at Fermi, all of these factors increased costs beyond initial projections. Detroit Edison calculated that even if Fermi 1 were successfully repaired and operated for its planned
Over its 30-year lifetime, it would never generate enough revenue to justify the investment. But abandoning the reactor meant abandoning the American Breeder Program's flagship project. It meant admitting that billions spent on breeder research had produced a technology that couldn't compete economically with conventional reactors. Political pressure favored attempting repair. The Atomic Energy Commission, which had invested heavily in breeder development, wanted Fermi 1 to succeed. Michigan politicians who had supported the project didn't want to see it fail. In June 1968, Power Reactor Development Company announced they would repair Fermi 1 and attempt to restart operations. The repair would take 2 years and cost $30 million. The book. While Fermi 1 sat idle, awaiting repair, a journalist named John Fuller was investigating the accident. Fuller had obtained documents through Freedom of Information Act requests. He had interviewed engineers who worked on the reactor. He had reviewed AEC safety studies that had predicted exactly the kind of accident that occurred. In 1975, Fuller published We Almost Lost Detroit, a book that exposed how close the Fermi 1 accident had come to catastrophe. Fuller's thesis was straightforward. If the sodium flow blockage had been more severe, if more fuel assemblies had melted, if the molten fuel had collected in a critical configuration, a secondary nuclear excursion could have occurred. Such an excursion might have generated enough energy to breach the reactor vessel. Molten fuel could have contacted water, creating a steam explosion. The containment building might have failed. Radioactive material could have been released to the environment. Detroit, 30 miles away, would have been in the path of the radioactive plume. Evacuation might have been necessary. 2 million people could have been displaced. Fuller's book was controversial. Nuclear industry representatives argued he exaggerated the risks. The actual accident had been contained safely. The worst-case scenarios Fuller described were speculative, based on accident progressions that didn't actually occur. But Fuller's core point was valid. Fermi 1 had experienced a serious accident, and the public had not been fully informed about the severity or the risks. The book's title, We Almost Lost Detroit, became a rallying cry for anti-nuclear activists. It crystallized fears about nuclear power in a single evocative phrase. Fermi 1, already a technical failure, became a political symbol.
Chapter 4: The Aftermath. The repairs to Fermi 1 were completed in July 1970, nearly 4 years after the accident. The damaged fuel assemblies had been removed and shipped to a reprocessing facility. The flow guide segments had been permanently secured with redesigned attachments. The primary sodium system had been drained, cleaned, and refilled. Thousands of hours of testing verified that all systems functioned normally. On October 6, 1970, Fermi 1 achieved criticality for the first time since the accident. The reactor that had melted down 4 years earlier was operational again. Power ascension testing resumed. Operators carefully increased reactor power, monitoring every parameter for any indication of problems.
By December 1970, Fermi 1 was operating at 100 megawatts thermal, one-third of design capacity. Everything appeared normal. Temperature profiles were uniform. Sodium flow was stable. No anomalies were detected. The reactor had been successfully repaired. The breeder dream was alive again. But the economic reality had changed. The economics. Between 1966 and 1970, the nuclear power industry had evolved. Light water reactors had become the standard for commercial power generation. Utilities were ordering them by the dozen. Construction costs were predictable. Operating experience was accumulating. The technology was proven. Breeder reactors remained experimental. Only a handful existed worldwide. Operating experience was limited, and every breeder that had been built had encountered serious problems. Fermi 1's accident had demonstrated the risks. Sodium cooling was complex and potentially dangerous. Fast neutron physics was difficult to control. Maintenance was expensive because of high radiation levels. Detroit Edison calculated the economics. Even operating successfully, Fermi 1 would generate electricity at a cost higher than conventional nuclear plants. The fuel breeding capability, which was supposed to provide economic advantage, was offset by higher operating and maintenance costs. The reactor that was built to demonstrate commercial viability was demonstrating the opposite. In August 1972, Detroit Edison announced that Fermi 1 would be permanently shut down. The reactor had operated for a total of approximately 30 days at significant power over its entire lifetime. It had never exceeded one-third of design capacity. It had generated a tiny fraction of the electricity originally projected. The $135 million investment, equivalent to over $1 billion in modern currency, was written off as a loss. The decommissioning. Shutting down a sodium-cooled breeder reactor was almost as complex as building one. The sodium coolant was radioactive from years of neutron exposure and contamination from the fuel damage. Approximately 500,000 pounds of radioactive sodium had to be removed from the primary and secondary cooling loops. Sodium cannot simply be drained and disposed of. It reacts violently with water and burns in air. It has to be
carefully neutralized before disposal. Engineers developed a process to react the sodium with steam in a controlled environment, converting it to sodium hydroxide. This process took months and required continuous monitoring to prevent runaway reactions. The fuel assemblies, both intact and damaged, were removed and shipped to reprocessing facilities. The reactor vessel was cleaned, removing residual sodium and contamination. By 1975, the reactor was defueled and the sodium was removed. But significant radioactive contamination remained in the reactor vessel and primary system components. The containment building and reactor systems would remain radioactive for decades. Complete decommissioning would be impossible until radiation levels decayed sufficiently to allow safe dismantlement. The decision was made to place Fermi 1 in a long-term storage configuration. The reactor would be sealed and mothballed to be fully decommissioned decades in the future when radiation had decayed to manageable levels. The facility today. The Fermi 1 containment building still stands on the shore of Lake Erie in Monroe County, Michigan. Adjacent to it is Fermi 2, a conventional light water reactor that began operation in 1988. Fermi 2 generates 1,150 megawatts of electricity, nearly 4 times what Fermi 1 was designed to produce. It operates reliably and economically. The contrast is stark. Fermi 1, using advanced experimental technology, failed. while Fermi 2, using conventional, proven technology, succeeds. Inside the Fermi 1 containment building, the reactor vessel remains. It's still too radioactive for workers to safely enter without extensive shielding and protection. Radiation levels in the reactive vessel exceed 1,000 roentgens per hour in some locations. The facility is maintained in a safe storage condition. Radiation monitoring ensures no leakage to the environment. Security prevents unauthorized access. But otherwise, the facility sits idle, a monument to nuclear ambition that exceeded engineering capability. Current plans call for complete decommissioning to begin around 2032, roughly 66 years after the accident. By then, radioactivity will have decayed enough to allow dismantlement without excessive radiation exposure to workers. The radioactive components, the reactive vessel, contaminated piping, structural materials that absorbed neutron radiation will be packaged and shipped to permanent disposal sites. The containment building will be demolished, the site will be remediated, and eventually the land where Fermi 1 stood will be returned to other uses. But for now, it remains. A sealed concrete sphere on the shore of Lake Erie, containing a reactor that came within hours of making 2 million people evacuate their homes. The breeder program. Fermi 1's failure didn't immediately kill the American breeder reactor program, but it severely damaged it. Other breeder projects continued through the 1970s and 1980s. The Clinch River breeder reactor in Tennessee. Fermi 1 was the first indication of these problems, but the nuclear industry, the AEC, and political supporters of breeder technology didn't accept the lesson until billions more had been spent and decades more had passed.
Chapter 5: The Cover-Up. The full story of how close Fermi 1 came to catastrophe didn't emerge until years after the accident, when documents were declassified and engineers who had worked on the reactor began speaking publicly. What became clear was that the October 1966 accident had been far more dangerous than initially disclosed, and that Power Reactor Development Company, Detroit Edison, and the Atomic Energy Commission had all minimized the severity to avoid public panic and political backlash. The worst case. Internal AEC documents obtained through Freedom of Information Act requests in the 1970s revealed that during the accident, engineers had calculated the probability of a catastrophic escalation. The scenario went like this. If additional fuel assemblies had melted, molten fuel could have slumped to the bottom of the reactor vessel. Under certain conditions, this molten fuel could have achieved a critical configuration, restarting the chain reaction. In a fast breeder reactor with no moderator, a critical mass of fuel in the wrong geometry can create a prompt critical excursion far more powerful than in a conventional reactor. The neutron multiplication happens so quickly that control is impossible. Such an excursion could generate a power spike of hundreds of thousands of megawatts in microseconds. The energy release would vaporize fuel, create a pressure wave, and potentially breach the reactor vessel. If the reactor vessel failed, molten fuel at 1,500 degrees Fahrenheit would contact the concrete and steel structures below. The thermal shock could cause steam explosions if any water were present. The containment building might fail. AEC analysts calculated that such a sequence, while unlikely, was physically possible. They estimated the probability at between 1% and 10% during the actual accident.
This meant that when Richard Schernbach and his crew were managing the crisis on October 5, 1966, there was a real, calculable chance that their damaged reactor could escalate into a catastrophic failure. They didn't know these calculations existed. They were managing the accident based on their training and the limited information available. But in Washington, AEC officials were watching the situation unfold and calculating evacuation zones. The evacuation plans. Classified documents revealed that during the evening of October 5, 1966, the AEC had requested that Michigan state officials review evacuation procedures for the Detroit metropolitan area. The request was phrased carefully. It didn't mention the Fermi 1 accident specifically. It was presented as a routine review of emergency preparedness. But Michigan emergency management officials understood. Fermi 1 had experienced some kind of accident. The AEC wanted to ensure evacuation plans were ready if conditions worsened. Evacuating Detroit would have been a logistical nightmare. 2 million people, limited transportation routes, cold October weather. Where would people go? How?
Where would they be housed? How long would the evacuation last? The plans existed, but had never been tested at scale. No one knew if they would work. The best estimate was that complete evacuation would take 24 to 48 hours under ideal conditions. Under panic conditions, it could take days. Fortunately, the evacuation never became necessary. By October 6th, conditions at Fermi 1 had stabilized. Core temperature was declining. The risk of further fuel damage was minimal. The emergency management review was quietly dropped. The public never knew how close they had come. News reports mentioned a malfunction at the Fermi reactor. No one said that evacuation plans had been reviewed. No one mentioned the worst-case scenarios being calculated in Washington. The disclosure battle. In 1974, 8 years after the accident, environmental groups filed suit demanding full disclosure of Fermi 1 accident reports. The AEC fought the disclosure. They argued that detailed accident analysis contained sensitive nuclear technology information that could be useful to foreign governments. They claimed that releasing worst-case scenarios would cause unnecessary public alarm. Federal courts sided with the environmental groups. The documents were declassified and released in 1975. The revelations were explosive. The accident had been far more severe than publicly acknowledged. The worst-case scenarios included catastrophic containment failure. And the company and regulators had deliberately minimized the danger in public statements. John Fuller used these documents extensively in We Almost Lost Detroit, creating a detailed narrative of how the accident unfolded and how close it came to disaster. The nuclear industry's response was defensive. They argued that worst-case scenarios were theoretical, based on conservative assumptions that overestimated risk. The actual accident had been safely contained. The systems worked as designed. This was technically true, but politically tone-deaf. The public didn't care about the distinction between what happened and what might have happened. They cared that they had been lied to about the severity. Trust in nuclear power, already declining after years of cost overruns and safety concerns, took another major hit. The pattern. Fermi 1 established a pattern that would repeat throughout nuclear history. Minimize the accident, control information, and preserve the industry's reputation at the expense of public trust. The same pattern appeared at 3 Mile Island in 1979. Initial reports described a minor malfunction. Only later did the full extent of core damage become public. The pattern appeared at Chernobyl in 1986, when Soviet authorities delayed acknowledgement for days while radiation spread across Europe. And the pattern appeared at Fukushima in 2011, when TEPCO and Japanese authorities repeatedly revised upward the severity of the accident as new information emerged. Each time, the motivation was understandable: avoid panic, prevent panic.
Overreaction. Maintain confidence in nuclear technology. But each time, the result was the same. When the truth eventually emerged, it destroyed more trust than transparency would have cost. Fermi 1 was perhaps the first time this pattern was clearly documented in the American nuclear program. It wouldn't be the last. The personal cost. The engineers who worked at Fermi 1 during and after the accident carried the experience for life. Richard Schernbach, the shift engineer who managed the crisis, never spoke publicly about the accident until the 1990s. When he finally gave interviews, he described the psychological burden of knowing what might have happened. "We didn't know about the worst-case scenarios at the time," he said. "We were just trying to stabilize the reactor and prevent more damage. Later, when I learned how close we came to a catastrophic failure, it was terrifying to think about. We made the right decisions, but we were also lucky." Other operators echoed this sentiment. They had performed their duties competently. They had followed procedures. They had brought the damaged reactor under control. But they had done so without knowing the full stakes. Some workers left the nuclear industry after Fermi 1. They couldn't reconcile the official narrative of safety with their personal experience of managing a partial meltdown. Others stayed, believing that the lessons from Fermi would make future reactors safer. They became advocates for improved safety culture, better training, and more honest communication about risks. But all of them carried the knowledge that on October 5, 1966, they had been responsible for a reactor that came dangerously close to making history in the worst possible way.
Chapter 6. The Legacy. Today, more than 50 years after the Fermi 1 accident, the reactor's legacy remains complex and contested. To critics of nuclear power, Fermi 1 represents everything wrong with the technology: experimental designs pushed into operation prematurely, regulators captured by the industry they regulate, companies prioritizing economics over safety, and a culture of secrecy that hid the truth until exposed by journalists and lawsuits. To defenders of nuclear power, Fermi 1 represents the inherent challenges of pioneering technology: unforeseen failure modes, lessons learned through experience, and the inevitable gap between theoretical design and practical operation. The fact that containment worked, that the accident was controlled, and that no one was injured demonstrates that safety systems functioned as intended. The technical lessons. The engineering community learned specific lessons from Fermi 1 that influenced subsequent reactor designs. Material selection matters. The zirconium bolt failure that caused the accident was predictable with better understanding of radiation damage to materials. Modern reactors use materials extensively tested for radiation resistance. Safety features can create new hazards. The flow guide that broke loose was installed as a safety device. Its failure demonstrated that adding safety systems without fully understanding their failure modes can increase risk rather than decrease it. Instrumentation must reflect core conditions. Fermi 1's instruments showed sodium temperature and flow, but couldn't directly indicate what was happening to the fuel.
Modern reactors have more comprehensive instrumentation that provides clearer indication of core status. Sodium cooling is inherently complex. The difficulties experienced at Fermi 1 and other sodium-cooled reactors led to the conclusion that sodium cooling, while theoretically superior, was practically too challenging for commercial deployment. These lessons were incorporated into later reactor designs, though often only after considerable resistance from designers who believed their systems were different or better. The economic lesson. Perhaps the most important lesson from Fermi 1 was economic. Complex technology isn't necessarily better technology. Breeder reactors were theoretically superior to light water reactors. They used fuel more efficiently. They generated plutonium. They promised unlimited energy. But they required exotic materials, complex cooling systems, and extensive maintenance. Every advantage in fuel efficiency was offset by disadvantages in construction cost, operational complexity, or safety margins. Light water reactors using simpler technology with more
Operational experience proved more economical. The market chose simplicity over sophistication. This lesson has relevance beyond nuclear power. Throughout history, industries have pursued complex solutions to problems that simpler technologies solved adequately. The sophisticated solution often fails to displace the conventional solution, not because it doesn't work, but because the additional complexity isn't worth the marginal improvement. Fermi 1 demonstrated this principle in the nuclear context. The regulatory legacy. The Fermi 1 accident influenced how nuclear facilities are regulated in ways both positive and negative. Positively, it demonstrated the need for thorough safety analysis before licensing new reactor types. The AEC's initial hesitation to approve Fermi 1 proved justified. Future experimental reactors faced more rigorous review. Negatively, it established the precedent of minimizing accident severity in public communications. The pattern of reassuring statements followed by gradual disclosure of worse news began at Fermi 1 and continued through subsequent accidents. When the Nuclear Regulatory Commission replaced the AEC in 1974, one stated goal was separating reactor regulation from reactor promotion. The AEC had been responsible for both advancing nuclear technology and for ensuring its safety, an inherent conflict of interest exposed by Fermi 1. The NRC, in theory at least, would regulate nuclear power without the promotional mission that had led the AEC to minimize Fermi 1's significance. The cultural impact. We Almost Lost Detroit became more than a book title. It became a cultural touchstone, a phrase that encapsulated fears about nuclear power in an era when those fears were becoming mainstream. The accident occurred in 1966, before 3 Mile Island and Chernobyl, when nuclear power was still generally accepted by the public, but it planted seeds of doubt that would grow over the following decades. The environmental movement emerging in the late 1960s and early 1970s seized on Fermi 1 as evidence that nuclear power was fundamentally unsafe. The fact that the accident had been hidden from the public reinforced suspicions that the nuclear industry couldn't be trusted. Musicians picked up the phrase. In 1976, Gil Scott-Heron released a song titled "We Almost Lost Detroit," bringing the Fermi 1 story to audiences who might never read John Fuller's book. The lyrics were damning. It stands out on a highway in Michigan. Workers came to shut it down.
It would have burned up everyone in Detroit if it wasn't for a worker who stepped outside the gate. This was poetic license. The accident didn't happen quite that way, but it captured the emotional truth. A reactor near a major city had nearly melted down, and only luck and skilled operators had prevented catastrophe. Today, the Fermi 1 containment building is barely noticeable from the highway. Most people driving past see Fermi 2's cooling towers and assume
that's the only nuclear facility on the site. Inside the sealed Fermi 1 containment, radiation continues to decay. Cobalt-60, with a half-life of 5.27 years, has decreased significantly since the reactor shut down in 1972. Cesium-137, with a half-life of 30.17 years, remains at elevated levels. Nickel-63, with a half-life of 100 years, will remain hazardous for centuries. The reactor vessel, activated by decades of neutron exposure, is itself a radiation source. Removing it will require cutting it into pieces small enough to handle remotely, packaging each piece in shielded containers, and transporting them to a permanent disposal facility. This work will cost tens of millions of dollars. It will take years, and it will generate hundreds of cubic meters of radioactive waste that will require disposal in a geological repository. The cost of decommissioning Fermi 1 will likely exceed the cost of building it. The reactor that was supposed to generate unlimited energy for pennies will ultimately have cost far more to dismantle than it ever produced in value. The final accounting. In purely economic terms, Fermi 1 was a disaster. $135 million invested in the 1950s and 1960s, equivalent to over $1 billion today. Operated for approximately 30 days at significant power, generated electricity worth a tiny fraction of the investment, left a contaminated facility that will cost millions more to decommission. In technical terms, Fermi 1 was a qualified failure. It demonstrated that sodium-cooled breeder reactors could operate, but also that they were far more complex and problematic than anticipated. The accident revealed design flaws that might have been discovered through better analysis. In safety terms, Fermi 1 was both a success and a failure. The containment worked. Radioactive release was prevented. No one was injured. But the accident should never have happened. The zirconium bolt failure was predictable. The flow guide design was inadequate. And the cultural normalization of operating with known defects created conditions for the accident. The question. One question remains. Could a Fermi 1 accident happen today? The answer is complex. Modern reactors have better materials, more comprehensive instrumentation, and more robust safety culture. The specific failure mode that occurred at Fermi 1, zirconium bolts breaking and a flow guide segment blocking cooling, is unlikely to recur. But the underlying vulnerabilities remain. Complex systems have unforeseen failure modes. Materials behave unexpectedly under extreme conditions. Safety features can create new hazards. And human organizations, even well-intentioned ones, minimize bad news and resist uncomfortable truths.
This specific accident won't happen, and no serious accident will happen, is where nuclear risk lives. Fermi 1 demonstrated that sophisticated engineering and multiple safety systems can still fail in ways designers didn't anticipate. Modern reactor designs claim to be inherently safe, unable to melt down regardless of operator error or equipment failure. These claims may be valid, but similar claims were made about Fermi 1, which was supposed to have multiple barriers preventing fuel damage. History suggests humility. Every generation of reactor designers believes their systems have solved the problems of previous generations. Every generation discovers new problems. There is no memorial to the Fermi 1 accident. No plaque explains what happened on October 5, 1966. Visitors to the Fermi 2 plant drive past the sealed Fermi 1 containment without knowing what it contains. This is perhaps appropriate. Fermi 1 killed no one. It injured no one. The radiation was contained. From a certain perspective, it was a success, a serious accident that was safely managed and controlled. But from another perspective, the absence of acknowledgement is a continuation of the minimization that began in 1966. The reactor that nearly required evacuating Detroit is treated as if it never happened. The reactor that demonstrated the limits of human ability to control nuclear processes sits sealed and silent, slowly decaying, waiting for the day when radiation levels drop enough to allow dismantlement. Inside that sealed building is approximately 500 tons of steel and concrete contaminated with isotopes that will remain hazardous for generations. It's the physical manifestation of nuclear power's paradox: immense energy density coupled with immense consequences when control fails. Fermi 1 didn't explode like Chernobyl. It didn't release significant radiation like Fukushima. It didn't even achieve the public awareness of 3 Mile Island. But it came close, dangerously close. Close enough that engineers calculated evacuation zones. Close enough that worst-case scenarios involved catastrophic containment failure. Close enough that 2 million people going about their lives 30 miles away might have found themselves fleeing their homes if the accident had progressed differently. We almost lost Detroit. We didn't. The containment held. The operators performed well. The accident was controlled. But almost is a dangerous word in nuclear power. Almost means barriers between safe operation and catastrophe are thinner than we want to believe. Almost means luck matters. Almost means next time might be different. The Fermi 1 reactor taught that lesson at a cost of $135 million and one partially melted core. The question is whether we learned it.